Okay. Where is the pointer? Okay. So this is chapter 2, chapter 3. Uh, I uh, I already started this chapter with the other section, so that's why uh, lecture is already recorded and available on the channel. But there is some mistake in that recording. Half of the lecture is okay, but half of the lecture is without video. So that's why I'm recording it again. uh, so this is CO3, and in this CO we have to look over these topics. First one, the set and its operations, and then the functions, sequences, and summations. We will see these topics one by one, and I hope that you already have some knowledge about sets from your previous classes when you were studying in your 10th grade or 11th grade. At that time, you studied something about sets, but you will see the things again. So here it is, the definition of the sets. And normally it is the first chapter of mathematics if you just remembered your previous studies at the level of 9th, 10th class or 11th class. So set is a word. Set is what? Set is a collection of objects, but unordered collection of objects. Unordered collection of objects means, just a minute, we can turn this light off and the visibility will be much better. Okay. So now set is a unordered collection of objects. This is a general definition, so that's why we are using this word object and unordered. So there is no ordering when elements or objects are in the set. It is unordered. They will be randomly placed in a set. And these objects are also called elements of sets, or you can call these elements the members of the set. These are all different sentences that you can say for the elements. So set is what now? It is a collection of objects, but unordered. And in this set, we have the elements, or you can say members of the set. And if you have the element, for example, this one, A, small a is an element in a set, capital A, then you can represent the existence of that element in that set with this mathematical notation like this. A belongs to A. This is what you are saying. You are saying that this element A is existing in the set A. And mathematically, you can represent it with this notation. And if it is not existing, then you can represent like A not belongs to capital A. So capital A, we will use in this chapter or in sets, we will use capital letters to represent sets, and we will use small letters to represent elements. Moving on, now we have different sets available in mathematics, but this is not the whole list. This is just a popular ones are just listed here. For example, we represent natural numbers with n. And what is natural number? Starts from 0, 1, 2, 3, and so on. It is an infinite set. And then we have the z, and in this z we have the negative numbers. And then we have the 0, and then we have the positive numbers. So z is a set of integers, negative integers and positive integers, including 0. And z plus is what? It is for the positive integers. And positive integers start from 1, 2, 3, and so on, infinite. Similarly, q is a set of rational numbers, and rational numbers will be in this format or in this form, p divided by q. It would be in this format. The elements in this set q would be like that. P divided by Q. And what is P? P belongs to Z, which is the set of integers, negative and positive. And Q is also belongs to Z. And other condition is that this Q would not equal to 0. And then we have the real numbers represented with R. Then R plus is positive real numbers, and you know that real number is the fractional numbers with decimal point. And then we have the C's. What is C? C is a set of complex numbers. And here in this set, you will have the elements like that, A plus B iota, or you can say A plus BI, where I is iota. So this A and B can be real numbers. They are basically real numbers. So you can imagine that 2 plus 3 iota, 5 plus 7 iota. So then you will have elements in this complex numbers in this format. And A, B are real numbers. And since this B, which is a real number, is the part or is multiplying with this iota. So that's why now you will say that this B is now imaginary part. Okay. Due to this combination with iota, now we have another title for this part of this equation or this number. And then I, what is the value of I is the square root of -1. So -1 and square root, what would be the result? That would be the value for the I. And then, okay, this walaikum assalam. So this is now the definition for the equality of sets. When two sets are normally equal, what is in your mind? If I will give you two sets, then if I ask you to show that both of these two sets are equal or not, what you will do? You will check the elements. You will compare the elements of set A with the set B, and if they are same, then you will say that both are. If they are same, then you will say that both are equal. Yeah. So this is the definition for the kids actually. So that's why I mentioned here, read it yourself. This is not a topic for mature persons. Anyhow, two sets are equal if they have the same elements. And how you can represent this definition mathematically like that. Mathematically, you can represent like that. For every x, where x is an element of set A or B, x belongs to A, double implication, x belongs to B, which means x belongs to A and also belongs to B. And then you can write the equality with this assignment operator. Here, this is not the assignment of right-hand side to the left-hand side. It is saying that A is equal to B, okay? In mathematics, not in, so this is not a programming language. And then we have a topic of Venn diagram. So there is a person, John Wayne, who gave this idea of Venn diagram in 1881. And what is Venn diagram? We use Venn diagram to represent different sets diagrammatically, graphically. So this is the only use of Venn diagram. We use Venn diagram to represent the connection or relationship between different sets graphically. So there is a universal set, and the letter for universal set is U. We represent, and universal set normally contains all type of numbers. The numbers that you see, that you saw here, all type of numbers are in the universe, in the universal set. So normally we represent this universal set in Venn diagram with a rectangle. Rectangle is fixed for this universal set. And the other set, the natural, the real, the Z, the Q, whatever the C, those sets you can represent with the other geometrical figures according to your choice, or with the circles, or with the circles. And if you want to represent the elements of some set, you can use the points. You can use the points. For example, here, this rectangle is for the universal set. And then you have this small circle represented with A. And then you have outer circle outside. What it is showing? It is saying that A is a subset of B. This Venn diagram is saying what? A is a subset of B, or you can say A, all the elements of A are existing in set B, are also existing in set B. All the elements of A are also existing in set B. So that is the definition of subset of, that is the definition of subset. If we have two sets A and B, if I want to say that set A is a subset of B, what it means? It means the elements of A, set A, are also existing in set B. So set B is a bigger set. And then you can say A is a subset of B. It is written here. If and only if every element of A is also an element of B. Okay. And you can represent it mathematically. A, this symbol is for subset, A subset B. Okay, this is the definition for the subset. And now moving on, we are going to see the finite set and the cardinality. Finite set. Generally, finite set means a set which has a fixed number of elements. A set which has a fixed number of elements. For example, if one set is containing 15 elements, that is fixed. Other is containing 25, that is fixed. There is no infinity. There is a limit that it is 15, it is 30, it is 100. So that is called finite. That is called finiteness or finite set. That set is the finite set. So now the definition. If there are exactly n distinct elements, distinct mean different. If there are exactly n distinct elements in S, which we have supposed here, and n is what? N is a positive integer. Non-negative means positive integer. Then we can say that this S is a finite set because n, it is containing n different elements, and that you can give the value to this n, 20, 25, 100, whatever. So that set contains 100 different elements, distant elements are like that. So that is called, this is the definition for the finite set. And then we have the cardinality. That n that you are saying, which is representing that how much elements that set is containing, this is called the cardinality. The other meaning for the cardinality is the size of the set. So size and cardinality is the same thing. And we can represent this cardinality with these parallel pipes. For example, if A is a set of odd positive integers less than 10. So in set A, we have less than 10. All numbers are less than 10, but they are odd positive, and they are positive and odd also. So then what is the cardinality of the set? This is the question. Then positive number starts from 1 and it will go up to 10. So 1, 3, 5, 7, 9. These are the odd ones. And it is 5. So the cardinality of this set is now 5. 5 elements, 5 odd elements. And what is the cardinality for the empty set, null set? So this is phi, or you can say it phi. It is up to you. So this is phi, and the cardinality of phi is what? 0, because null set or empty set normally do not have any element. Null set normally does not have any element in it. Now we have another definition. What is the definition for infinite? So you have seen the definition for the finite. Then you can give the definition for the infinite. So the set which is not finite is the definition for the infinite. Easy way. When you have the understanding of finite, only then you can give this definition. The set which is not finite is infinite, because you have the understanding of finite. If you don't have the understanding of finite, then this definition will not work. Okay, then this definition will not work. Then maybe you have to write some more sentences. Anyhow, it's okay, because here we have the definition for the finite. So here, set of positive integers is infinite. So positive integers start from 1 and it will go on and go on. As there is no limit, so we will not stop, we will go on. So that is called infinity. We will go on to the numbers where we will. So that's why the set of positive numbers, the set of natural numbers, mostly all the sets that you see here, the set of the Z, the Z plus, the Q, whatever it is, almost, if you will not give any limit, the last ending limit, then it will be infinite. Now, we will see the definition for the power set, but I have mentioned, read it yourself because it is not difficult. You have the definition of the subset now. If you have that definition, then you can understand this power set. If you are given with a set S, suppose we have a set S, the power set S is the set of, what is the power set of this S? It is saying that it would be the set of all subsets of that set S. So you have a set S with some elements. And then you will calculate all its possible subsets. All its possible subsets, and you will keep those all subsets in another set as an answer. So this set with this collection of subsets is now called the power set of that given set. For example, and you can represent the power set of S with this P, okay? P and then the name for the set. And what, for example, here, P, we are going to see the power set of this set, and the set elements are 0, 1, 2, and P of S is the notation that we have here. It is easy. So the power set will contain, first, you have to include the null set phi, you have to include phi and the set itself by default as a subset, as a collection of the subsets. So that's why this is, whenever you are going to calculate the subset of a set, so this would be the part, the phi and the whole set itself. So this phi is the part and this whole set is the part. Now, what is the other one? Okay, 0 and then 1, then 2 individually, and then make this 0 with 1, 0 with 2, 1 with 2, and the whole. And all these things are written here. Yes.
We change the order.
Order doesn't matter.
If you want the new section, for example, 1, 2, it was 2, 1, it's not new section.
This is a new chapter now. This is CO3. We have started CO3.
Yeah.
So what you are asking?
No, I mean for 1, 2, for subset 1, 2. If it was 2, 1, 1, will be new subset or?
It is new chapter. It is a new chapter.
No, not chapter, different. Subset 1, 2.
Okay.
Yeah.
1, 2, and
Yes.
2, 1?
Yeah.
No, that you don't have to do 2, 1. You have to go with the order. Okay. So anyhow, and if some set will be given to you, if some set will be given to you, how can you calculate that what would be the number of subset possible for this set? This is the formula, 2 raised power n. So here you have 3 elements. So 2 raised power 3, you will have the 8. So there are 8 subsets possible for this set, which is containing 3 elements. So then you have to calculate all those 3. And it is, if you just count these, 1, 2, 3, 4, 5, 6, 7, and 8. So 8, these are it. Anyhow, moving forward, Cartesian product. What is Cartesian product? It is easy. Cartesian product would be at least between 2 sets. At least between 2 sets. It would not be with 1 set. Yes, you can say set with itself, then it is okay. So if you have 2 sets A and B, the Cartesian product of A and B you can represent with like A cross B. And what type of elements would be in this A cross B? It will contain ordered pairs. It will contain ordered pairs like this A comma B, and A would be the element of A and this B would be the element of B. So this is also in order. A would be the element of this A set and B would be the element of this B set. And now this whole story you can write mathematically like this in 1 line. This is also a definition. 1 line mathematical definition. By the way, I saw the negation for the unique existence and there is no any symbol. You have to say it theoretically. If you are going to apply the negation over there exists and unique symbol, there is no symbol available. You have to discuss it theoretically. So this is the answer. Some persons convert those unique quantifier into their existence forever. But then the answer is that we have those symbols and there is no new symbol for the negation of unique existence. So now coming back, A cross B. So in this A, we will have the pair AB. This pipe means such that. So AB, we will have the pairs like A comma B such that A will belong to A and B will belong to set B. This A and talking about this set A and B. Now example, if we have the set A and the set B, now we have to calculate what is the Cartesian product of these 2 sets. It's easy. A cross B would be just take first element and make pairs with all these elements 1 by 1. So 1A, 1B, 1C, and then take this second, and then 2A, 2B, 2C, and you have these pairs. And in all these pairs, the first element belongs to set A, and the second element belongs to set B. And same is here. What is the Cartesian product for A cross B cross C? Now you have 3 sets. 3 sets. So you have to do the things again. But if you have 3 sets and it is represent now your answer, each element of this Cartesian product will contain 3 elements. It is not a pair now. It is now, you can call it triplet or triple. All the elements of this Cartesian product will contain 3 elements. This is the thing that you have to keep it in your mind. You don't have to start with single and then double elements, which is a pair, and then triple, and then you will make yourself confused. So all the elements has 3. And how it will? 0, 0, and then 1. And this 1 with 0, 1, and 2 separately, individually. 0, 1, 0, 0, 1, 1, 0, 1, 2, and all these things are mentioned here. And then you can take 0 and 2. And then 0 to 0, 0 to 1, 0 to 2, and so on. So this is easy. You can read it and understand it by yourself. It's not difficult. Now, what is relation? Hmm.
The order.
Order is not order. Yes, order is important. That the order. This order is matters. That this should be the element of A. This should be the element of B, and this should be the element of C. This order matters.
I mean, but if you have A cross B and B cross A, the results are considered the same.
Why you are going for the A cross B and then B cross A? It is not asked. If you will do A cross B first and B cross C first, then you will get pairs, not triples. Then you will get pairs like that with two elements. That would be wrong. So A cross B and B cross, for example, if you are saying that you will calculate A cross B first, and then then whatever the answer, then you will see, okay, that, or what do you say, B cross C. And then if you will do that, it is not triple, it is a pair with two values. And when you will do that, it is wrong, because here you have the three values in each unit. What is relation? So now, if you know, we know the definition of the subset, and we also know the definition of the Cartesian product. And if you know them, then you can understand what is relation. A subset, maybe we can say it R, a subset of a Cartesian product, AB. We have two sets A and B, and so we have calculated their Cartesian product. And then we have some answer for the Cartesian product. And then if there is a subset, R, if R is a subset of the Cartesian product, we can call that subset a relation from set A to set B. Okay? If we have a subset of a Cartesian product of A cross B, what I'm saying, for example, we have this set A and we have this set B with these elements. Suppose the Cartesian product of these is containing maybe, I don't know, maybe 15 elements. Just suppose the Cartesian product A cross B is containing these, suppose 10 elements. Now, if I have something here which is also these pairs, but it is only this portion, and I am keeping it here, then this portion is the subset of this whole Cartesian product. This is true? This is true or not? I am saying that this is A cross B and the answer is containing 10 elements. And I have just this portion, I have another part, not this one. I have another part, and here the elements and here the elements are similar as the elements existing here. Can I say that this is the subset of this whole Cartesian product?
Yes.
If it is yes, then I can say that this is the relation, which is the subset. This is the relation for this Cartesian product, and this is a Cartesian product for the A and B. So I can say this is the relation from the set A to the set B, nothing else. This is what written here. And the elements of R, which is a relation, and the elements of R would be ordered pair. Yes, we know that because this relation, this R, will contain the pairs, which contain the pairs or triples, or which contain the elements of this Cartesian product. So that would be ordered automatically. And the first element will belong to A and the second element will belong to B, because in this definition we are taking only two sets. We are not taking three. If it would be three, then we will say the third will belong to C. So this is an example. For example, this R, and it is the curly bracket here, and it is ending here. And in that you have this element, comma, the second, third, and you have these elements. And this, and it is saying this R is a relation from set ABC to set 0, 1, 2, 3. If you will calculate the Cartesian product of these two sets, if it is A and if it is B, it will be huge. But if this is a simply small portion from the Cartesian product of these two sets, so then you can say this R is a relation from this set A to this set B. And a relation from a set A to itself. Here you have the set A and here you again have the set A. If you are taking Cartesian product of a set with itself, A cross A, A cross A. If a relation from a set A to itself, if you have the situation like that, A cross A, and if you have some subset, if you have some relation, then you can say that relation on A. Relation on A, or relation from the set A to itself, you can also say in this way. These are some practice questions, and I will advise you to practice these questions, because maybe I will give one question from these exercises in the midterm or in the final term. And if you will not do the exercise of these questions, then you will say the hadha sawal mushkil. And then you will say, this is an unseen question. Okay. Set operations now, according to the CEO. So, set operation. First, we will see the definition for the union. This is easy. If you have two sets A and B, what is the union? The union of two sets A and B, we can represent with A and then union B. This is the mathematics, you know that. And this union will contain either the elements in A or the elements from B or the both. So this is the definition. And mathematically, you can write it like that. This is the definition of union. A union B will have the elements X, and X can belong to A or X can belong to B. And the meaning of or is it can belong to both also. Simply intersection. Okay, that is also easy. If you have two sets A and B, the intersection can be represented by this one. And what it means, you have to select the common elements from both the sets. So this set will contain those elements which will exist in both sets, A and B. The elements which will exist in A and also in B, they are the intersection of those sets. And mathematically, you can write it here, and only the AND operator is between them. It can contain elements X and X must belong to A and X must belong to B. That is compulsory condition. Anyhow, I hope that you already know that. Now, what is disjoint? By the way, disjoint normally means different. Not exactly different, but you can take it different. Joint normally, so this is joint. These two things are now joint. Disjoint means separate. But here you can take it different. So two sets are called disjoint if their intersection is empty. If you have two sets A and B, and if the intersection is empty, it means that both are different sets. Separated, you can, both are different sets. So if the intersection of two sets is empty, then it means that those two sets are called disjoint sets. Now the definition for the difference. A minus B. We can represent the difference of two sets like A and B with A minus B. A minus B. This is the mathematical representation. And what it means? It means that you have to remove the elements of B from A, and whatever left in A, that would be the answer for this A minus B. You have to remove the elements, all elements of B from this A, and whatever will be left in A, that would be the answer for this A minus B. And if you will do B minus A, you have to remove the elements of A from B, and whatever elements left in B, that would be the answer for B minus A. So that is the definition. A minus B is the set containing those elements that are in A, that are existing in B, but not in B. So the elements of B will be removed, and only the elements of A will remain. Okay. We can also say the difference of AB with another title, that is complement of B with respect to A. So A minus B, can we say complement of B with respect to A, like that? Don't say A to B, no. Complement of B with respect to A. So this is also another title for the difference. And mathematically, you can say it A minus B is equal to, it will contain elements. For example, X will belong to A and not belongs to B. This is the mathematical definition of this theoretical statements written here. So if you will give me this, if you will give this line to a mathematician, he will understand. He doesn't need this whole story. He only needs this line. And then what is complement? Okay, we have seen complement here, but now we have the definition, proper definition for complement. If we have a universal set U, and you know that what is U, containing all type of numbers, natural, real, rational, complex, all numbers are there in the universal. The complement of the set A, we can represent it with A bar, this small line over it, this small, which is called bar, A bar. We can represent complement of a set A with A bar. Is the complement of A with respect to U. So this complement that you will calculate, A bar is what? It means that it will have some results, it will have some elements that you are calling it complement of A. It is complement of A with respect to universal set U. This universal set, which I told you earlier. And you can represent the complement of set A like this, U minus A. It is same as the difference, nothing else. But we have the universal set. This representation is same as A minus B. But here we have the A and here we have the U, universal set first. And we have to remove the elements of A from this universal set. And whatever the elements left in U, that would be the result for this A bar. For this A bar. And mathematically, you can write it as A bar is equal to, it will contain elements that belongs to U and such that not belongs to A. Okay. These are the different rules for these sets. It's similar. A intersection U, it is equivalent to A. A union null set, it is equivalent to A. These are called identity laws. Similarly, A union U, which is a universal set, okay? A union U, you will have the universal set. A intersection null, you will have the null domination law. So you have to read these laws and keep it in your mind. And this will help you to evaluate different problems which are coming here. Now, example 10, use set builder notation and logical equivalences. Logical equivalences that you have seen in chapter 1 and 2 in the tables. The left hand side is equal to the right hand side. To establish the first De Morgan law, first De Morgan law is written here. A intersection B complement is equal to A complement union B complement. This is written here, De Morgan's law. Here, maybe this one, A intersection B complement is equal to A complement union B complement. So this question is saying that prove that this left hand side is equal to right hand side using builder notation and logical equivalences. The equations that you have seen in the previous chapters, by using those equations, you can replace the statements. This is called logical equivalence or the builder notations. This is the builder notation actually. Whatever here it is written, it is basically the builder notation. Or you can say, okay, this one is equal to that one, this one, okay, that is also the definition. You can build your arguments by using some mathematical notations, that is called builder notation. Okay, how we can prove it? We will take the left hand side, we will do something with the left hand side, we will change something in it, we will use different things, and we will try to transform that left hand side into the right hand side. And if we will be successful, then we can say that this De Morgan law is now the left hand side is equal to the right hand side. Now it's okay. Now it is proved. So we will start with this left hand side, A intersection B complement. And here we are writing something, which is basically its definition. What it is, A intersection B. If you have two sets A and B, and if you are taking intersection, you will take the common elements between those two sets. And if you will take the bar, what it means? U minus or whatever. So now, due to this complement, you don't have those common. It will be removed. It will be removed. So, okay, then A intersection B and complement, it will contain such elements X, such that X will not belongs to A intersection B. Is it okay or not? This is not belong is due to this complement. Otherwise, I know that A intersection B, you will have some common element X that will belong to A intersection B. But you have the complement, which is the opposite. Now you don't. Now it is not belonging to. So this is what you are writing. You are writing the definition for this complement, which you are mentioning here by definition of complement. And then what? So now you want, because here now we are changing this not belong into belong. And when, for example, if you are changing this X belongs to A intersection B, then this one and this one is not equal, because this is, and but if you will put negation outside this one, now this statement is equal to this one. Okay or not? Correct or not? Because it is not belong. Now belong and then negation, that will be opposite. So now this is equal to this one. Okay. By definition of does not belong symbol. So we have changed this does not belong symbol into the form of a negation, nothing else. And then do we have intersection here? No. Okay. If X belongs to A intersection B, leave this negation ahead. Just try to understand what it is saying. X belongs to A intersection B. Whatever the elements I will have, those are the common elements, exist in A and also exist in B. So I am just writing that X will exist in A and also X will exist in B. Nothing else. So I am just rewriting this intersection. I am opening the definition of this intersection.
Distribution.
It is only mentioned that by definition of intersection, we are not using any logical equivalences. We are just using the definition of intersection. If this is something, then what it means? It means that X will belongs to A and also that X will belong to B. So we are simply using the definition. The rest of the things are same. That negation is same. We are not touching that negation symbol, etc. We are just touching this internal portion, this one. Okay. Then what? Now we have the negation, and here we have something, and then we have something. By the first law of De Morgan, by the first De Morgan law for logical equivalences. Now using De Morgan law, which means negation P and Q from those previous tables. I don't want to go there. Negation P and Q is equivalent to negation P or negation Q. That is the first De Morgan law. You can just go into that table. It would be on slide 42. Okay. This slide 42 is in my mind because when I prepared your lecture at home, so I know that this is slide 42. I went back and I saw that table was on slide 2. So that's why that slide number 42 is in my mind. I'm not a Dr. Zakir Naik, okay? No, actually it is not too much. He is just expert in that particular one field. If you will do that thing, you will also be like Dr. Zakir Naik. He's not doing anything else.
The number of page and the number of the.
Yeah, this is what I am saying. Because he is always doing that thing, that one direction. He has one direction. Maybe here in Saudi Arabia, you maybe give some importance to Dr. Zakir Naik, but he is belonging to our area. We know many other scholars there. And you also know many other scholars in your areas. But he is no doubt memory-wise, he's good. So anyhow, coming back. So first, so this is negation P and so this is that law we used. And now it is becoming negation P or negation Q. It is that form. So now we use this first De Morgan law, and then we are negation P, which is this one, which is negation X belongs to A, or negation X belongs to B, like that. Okay. And then what? By definition of does not belongs to symbol. Now we are converting this negation again into that symbol not belongs to. So this is negation X belongs to A, and we have the negation. It means I can write it X not belongs to A. I can write it or not, because it is equal. And then, okay, or, and then negation X belongs to B. Okay, X not belongs to B due to that negation. And then by definition of complement. Allah Akbar. So
there's a complement of B.
no, sometime your mind stopped. I'm not thinking actually. Due to Som or Rosa, whatever, due to Som, fasting, sometime your mind just stopped. So that was the situation actually. It stopped. It was not thinking. It just stopped. So that's why I became silent. And it only happens in during these fasting days, because you don't have the concentration then in the fasting. You have the stoppage again and again, breaks. Allah. Okay. X not belong to A. If I say that this is the set A, and you have to calculate the complement of that set A, you will do what? With universal set, you will do what? You will remove the elements of A from universal set. And whatever the left in universal set, that is U minus A. But you can now say it is now A bar. It is now A complement. This is what you will say. The elements of A, which were the X of A, then now that those X are not available in A bar. So now X not belongs to A. How can I say A if I am using this belong symbol? X belongs to not A. Not A, you mean that in not in bar in A complement, you don't have the elements of A in it. Okay, you don't have. What is actually A complement means? A complement means the elements of A are not there. And this is what X not belongs to A. This is basically the same thing. So you have just used the definition of complement, and you have converted this not belongs into belong. And then what? Okay, this one or this one. So now X belongs to A bar or X belongs to B bar. So now by definition of union, okay, X belongs to A bar union B bar, because this R symbol is equal to union and AND symbol is equal to what? Intersection. Okay. And now this is what we are saying that we have elements X and X belongs to A bar union B bar, which is equal to this one, A bar union B bar. And this was the right hand side. So this is the proof from left hand side to the right hand side. And here we used first De Morgan law, not second, okay? This line is not needed anyhow. Now this example is the same, and it is containing theoretical discussion. So this is the mathematical proof. If you will discuss it in sentences like this, I use this one, that one, that would be the answer. So it is same. This is same, this one and that one is same, but it is written in sentences. And here you have totally short way of mathematics. So that's why I've just mentioned, read it yourself. It is not different. You will say definition of complement and De Morgan's law. So it is theoretically written.
So you can use it in Jam?
Yes, you can.
Yes, theoretic.
I think it would be difficult. That would be easy. How it is? Is it like that, or you will feel easiness in this one or in this one? First one is better, I think. Okay, whatever you will do, that would be your approach. Okay, then now definition 6, union of collection of sets. If you have more than, if you have collection of sets like A1, A2, and so on, AN, then what would be the union? That union, you can represent it with capital U, and it starts from I is equal to 1 to N, which is the last N. and it would AI, and here A1 union A2, it would be chain. So union of collection of sets is the set that contains those elements that are members of at least one set in the collection. So this union, which is a union of collection of sets, what is the minimum condition for this union? The minimum condition would be it will contain at least the element of one set, or maybe this one or that one, maybe A7, maybe 8, maybe A3. At least it will contain the element of one set. It can contain element of A1, A3, and A7. It will contain the elements from all the sets, but at least element from one set. This is what mentioned here. Intersection of collection of, okay, and this is for finite sets and this is for infinite sets. And I is equal to 1 to infinity. And now intersection of collection of sets. Again, now you can represent intersection with this symbol. I is equal to 1 to n, AI. And intersection, what would be the minimum condition for the intersection now? It will contain elements of all, because intersection is and. Good. Because the intersection is and, you have to include elements of all the sets. And this is for finite, and for infinite sets it can also happen. You have the infinity. Okay, I think this is the last slide. Set operation, bit strings for the sets. So we have one set, this containing 1, 2, 3, 4, 5, and another set 1, 3, 5, 9. And the bit strings for this set, this and this are, this is for the first one, and this is for the second one. Use bit strings to find the union and intersection of these sets. So you have to find the union and intersection of these two sets, where universal set U is starting from here and ending here. 1, 2, 3, 4, 5, 10. So universal set contains 10 bits, and this is the position of the bits. First position, second, third, fourth, fifth, up to 10. And this is a set representing the position. This is the set A, and here first bit, second, third, fourth, and fifth are active, are on, which you are seeing here. 1, 2, 3, 4, 5 are on, and rest of the 5 bits are off, because universal set has 10 bits. So each set can contain maximum 10 bits. And according to this representation, set A has this position of 10 bits. And then if this is set B, and according to 10 bits, 1, 3, 5, and 7. So this is the first, this is third, this is fifth, this is 7, and then 9. So 1, 3, 5, 7, and 9 are active, are on, are true, you can say. Now you have the understanding of question. Okay, now you have to calculate the union and intersection. So you can place the first bit first and then second bit and do the union. And union is what? OR. Apply the OR operator and you will have some result. You don't have to sub plus add. It is OR. If you have 0 and then the second bit is 1, answer is 1. 1, 1, 1. Yeah, okay, it's plus. It's plus, okay. So, and an intersection, so now it's easy. So now it's easy. So for example, here in these 2 bits, when you applied OR, you have this result. After this first bit with this first bit, this second bit with this second bit, this third bit with this third bit, this fourth 0, 0, 0. So you will go like that. You will go like that. And then you have the result like that. And then you have to represent it now 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5 is there. And then 7 and 9 is there. So that would be the answer. Okay, then you have to convert it again. And similarly for AND, okay, 1 and then 1, you have the 1. Similarly, okay, 0, this is fifth one. And this might be fifth one. And here might be this fifth one. And this is the result. And here 1, 3, and 5. Okay, that's the result. So that's easy. Union and intersection. And now these are the practice questions that you have to do again. And inshallah, I will start here in the next week. And we will try to finish this CO3 at the end of this week. Inshallah.